Hi there. Let me take a few minutes and do one complete question from beginning to end using a one sample confidence interval for a population mean. So I have taken a random sample, a simple random sample of 20 pennies from our class penny box. And again, I want to construct a confidence interval for the true population mean date on the pennies in the penny box. So you're actually looking at the 20 pennies that I selected by an SRS from the penny box. So I have put those dates into my calculator. Let's start using them. So here we go. First of all, our conditions. We need randomness. So this is indeed a simple random sample. Something to consider, not all questions will involve SRSs. So it's important that if the question indicates that all you have is a random sample, under your randomness condition, just indicate that you have a random sample. Don't just assume that it's a simple random sample. In this case, though, we really do have a simple random sample. So the independence condition, 10 times my sample size of 20 is 200, and that's well less than the population size of pennies within the penny box, that's 518. So now notice, the sample size is 20, that's less than or equal to 30, so the central limit theorem doesn't apply. Even when you have a smaller sample size than 30, the normality condition can still be satisfied by inspecting the actual values in your sample. So if the sample size is quite small, let's say less than 15, then you want to graph your sample, and you want your sample graph to be reasonably symmetric. You don't want to see any outliers in order for you to believe that the normality condition is satisfied. Now, if you have a sample that's a little bit bigger, let's say it's between 15 and 30 like ours, a sample size of 20, then as long as you don't have any outliers and you don't want any extreme skewness, so you could see a little skewness one direction or the other, but as long as it's not particularly extreme, then again you can consider that the normality condition is satisfied. So we definitely have our randomness. We definitely have satisfied independence. Here is our situation at a sample size of 20. So I want to make sure that I don't have any outliers and I don't want to see any extreme skewness. So in order to verify that, you really do need to build a graph. So here we go. I've entered the data into list 1 of the graphing calculator, so I'm going to start by running the one variable statistics on it. So the sample mean is 1990.9. One of the ways that I can consider whether the data may be skewed or not is to compare the mean and the median. So if I scroll down to the bottom here, the mean is relatively close to the median. The median is 1990.5. Again, looking at the one variable statistics, I can see the minimum and the maximum of 1970 and 2005. So I have already used those in order to set up a good window here. So I know that you could use the Zoom 9 option on your graphing calculator, but I like to have a little bit more control of my window. So my minimum, I went a little less than the minimum in my data set and a little higher than the maximum in my data set. I set a scale of 5. So then notice I've turned on 2 plots. Plot number 1 is turned on and it is set to the histogram option using list 1. Plot number 2 is also turned on and I set it to the box and whisker plot option using list 1. So the reason that this is particularly convenient, the box and whisker plot option that we chose will automatically show us and calculate whether or not there are any outliers. And in these data, there are no outliers in this sample of size 20. So when I look at that graph, it doesn't seem particularly skewed in a severe way in either direction. I wouldn't really describe it as normal. It's not particularly symmetric. But again, in terms of our terminology, I don't see any outliers. I know that for sure, and I don't see any extreme skewness in either direction. So even though the central limit theorem here doesn't apply, I can still proceed by saying that my normality condition is approximately satisfied here. So if we go back, again, looking at the conditions, I have my randomness condition with no problem, the independence condition with no problem. So again, with a sample size of 20, there is no extreme skewness and there are no outliers. So with n equal to 20, we can say that x bar is approximately normally distributed. That word approximately, though, is really important. It's approximately normally distributed. And now we can proceed. So our confidence interval is constructed by taking our sample mean, adding and subtracting our critical value. That's how many standard deviations above and below the mean I want to go in order to build my boundaries for my confidence interval. And then I need the standard error of the mean. That's also the standard deviation of the sampling distribution for the mean. There we go. So let's go back to our one variable statistics and find the values that we need. I don't quite recall them. So I'll run one variable statistics again on my list 1. So my mean is 1990.9 and my sample standard deviation is 10.3. So here we go. My sample mean is 1990.9. We'll come back and grab our critical value in just a second. So remember the way that the standard error of the mean or the standard deviation of the sampling distribution, the way that that is calculated here, we are going to use the sample standard deviation from the sample of size 20. So we want to take that sample value, which again, forgive me, it was 10.3. We're going to take that sample standard deviation, so we're acting as if we don't know the population standard deviation, and we're going to divide by the square root of our sample size. So that expression, again, there are two ways to name it. That is the standard deviation of the sampling distribution for x bar. That's also the standard error of the mean. And we have to determine our critical value. But because we are using here the sample standard deviation, we need to use t-scores. Because now there are two values, both the sample mean and the sample standard deviation, now that both of those are unknown, we have to use t-scores in order to allow for a little extra variability when we build our confidence interval. So again, recall what that means. Let's say we want a 95% confidence interval. Again, that's a very typical level of confidence. So very good. That means I want to capture the variability in the middle 95% of the sampling distribution. So up here is my critical value, the t star that I would like to find. So again, I need to figure out how many standard deviations above and below the mean I need to go to capture all of that variability. So remember, whether you are using the INVT command or the INVT calculator program, what you have to enter is the area under the curve from this location where t star is, where our critical value is. So remember, if we're looking at the middle 95% of the distribution, then we are ignoring, if you will, 5% of the distribution, the lowest 2.5%, and the highest 2.5%. So, in fact, the total area underneath my critical value is 97.5%. That's what I want to enter in order to find my critical value. And notice that I also have a degree of freedom here that I have to account for. My sample size is 20. So that means the degree of freedom often approximated or written as DF. That would be 20, take away 1. That's 19. So when I find my critical value on my calculator, again, if you don't have this command, if I press second variables, I have the invt command. If you don't have that, then you need the invt program. So let's go down and grab that command here. Here we go. So the area you want to put in, whether you're using the program or the command, is the 0.975. And then our degrees of freedom are 19. We'll paste that to the home screen. Our critical value, we'll call it 2.093. So that tells me, starting from my sample mean, I want to add and subtract 2.093 of my standard errors for the mean above and below my sample mean in order to create the boundaries for my confidence interval. So I'm going to go ahead and type that also into my calculator here. So from the home screen, 1990.9. I'll go ahead and add the 2.093 times the 10.3 divided by the square root of 20. There we go. Oops. Hold on just a second there. Not quite what I want, forgive me. Got the parentheses in the wrong location. There we go. That's the 10.3 divided by the square root of 20. There we go. So my upper boundary is 1995. We'll call it 1995.7. So I'm going to go ahead and press second enter to bring the command that I just typed into the calculator to bring it back. And I'm just going to edit it by going back and changing my addition sign to subtraction. And that way I can very quickly get my lower boundary also without taking the time to enter all of that back into my calculator. Very good. So I've got, well, let's go 2 decimal places, 1986.08. I'm going to write that down and I'll show you what I've written down. The upper boundary is 1995.72. There we go. So our level of confidence is 95%. So in order to interpret this, we would say that we are 95% confident that the population mean penny date is between 1986.08 and 1995.72. So let's talk about the important parts to include in a confidence interval. You need to have your level. That's very important. You should name the parameter that you are working with. You're working with the population mean. So you should put that in context. That's very important. And then, of course, you should give your boundaries for your confidence interval. That is the interpretation of the confidence interval. Just briefly, remember what the level means. The level means that we have created this confidence interval using a process or a method where if I repeated it many, many times using exactly this sample size of 20 and repeated this over and over again, about 95% of the intervals that we calculate will capture the true population mean. And notice we do know the true population mean in our penny box. This 95% confidence interval has in fact captured the truth, which is just a little above 1989. So there we go. That's one complete question from beginning to end in all of the detail of all the pieces, the little things to consider, to graph, the conditions, the way to show your work, the way to interpret, all the pieces that are really critical to understand when you're building a confidence interval. Hope this has been helpful.